Hey, so I guess, yeah, good afternoon, everyone. Right now it's afternoon in Houston. I guess it's kind of late in Italy, where our distinguished speaker is today. My name is Rahman Dus Mohammadi. I'm an assistant research professor at RI.SE. Welcome everyone to today's distinguished speaker series for wireless. Before I actually introduce our distinguished speaker today, just a few logistics. Um, for any questions during the talk, please leave it at the Q&A section, and I will leave it to our speaker, and we can have a discussion there. So let's hop right into it. So our speaker today is Professor Luca Mottola. He is an associate professor at Politecnico di Milano in Italy. He is also a senior researcher at Sweden Research Institute, known as RISE. He also have multiple other appointments and has held multiple positions and visiting positions at other institutions, such as NXP Technologies, Uppsala University, among others. He has won numerous awards, including the Google Research Faculty Award, ACM SIG Mobile Highlight Research Highlight, among others, as well as many Best Paper Award and Best Paper candidates, including at ACM Mobicom and Census. He was the general chair of IPSN 2018. He's also the co-chair of many conferences, including Mobisis this year. He is also the associate editor of ACM Transactional Mobile Computing and Sensor Networks as well. Dr. Mottola's research interest is on modern networked embedded systems, and I believe the topic of his talk today is about drones, specifically drone technology, and we're all excited to hear about it. So again, I would like to welcome you, Professor Mottola, and without further ado, the floor is yours.
Thank you, and thank you for the introduction. Welcome, everyone. I'm actually really excited to be here talking about our work on using robotic drones as a mobile computing platform. Now, rapid disclaimer is that besides the need to work from home due to the pandemic, it's evening here and I'm home with the whole family, including our two small kids who are 3 and 2 years old. So if you hear some noise in the background, that's the reason, and I apologize for that in advance. So to start off, I just want to spend a few words about myself, in addition to the nice introduction. As it was mentioned already, right now I have basically 3 affiliations besides the one at Politecnico. I'm also associated with RI.SE Research Institute of Sweden and Uppsala University. The reason why I'm mentioning this is because you'll see in the rest of the talk how like different contamination that I've experienced over time at these different places have come together in our work in this specific domain. More generally, I'm interested in developing systems that interact with the environment. I started working on wireless sensor networks more or less 10 years ago. Then overnight, they told us to call it Internet of Things. So I've been working on that too. And then I slowly transitioned into mobile robotics up to, poking into nano satellites more recently. If you're curious about what we do more generally, you can check out the website of our lab at www.neslab.it. So aerial drones have been on the hype for a number of years by now, and there are many different angles you can look at this technology. So you might be wondering, are aerial drones a form of robot? Well, actually, that's not really the case, or at least if you ask a robotics person, that person would probably answer that aerial drones are not really robots because they lack some of the fundamental features that those people try and achieve in the robotics field. For example, aerial drones right now do not show much autonomy in their behavior. Arguably, what we can achieve in a real world deployment in terms of autonomous behavior is not much more than waypoint navigation, which is kind of a trivial form of autonomous behavior. And most importantly, very few aerial drone platforms are able to change their behavior, to adapt their way of achieving certain tasks depending on the readings of certain application sensors. So there's overall little intelligent behavior that can be achieved, at least in real deployments. So if at all, we can probably consider drones as a form of crude robotics, if at all, again. Of course, you have probably seen all those YouTube videos where drones are shown to be juggling with balls, playing pianos. That's another way to look at that technology. Aerial drones are a formidable platform to study the dynamics of complex systems. In that kind of research area, the focus is on achieving very accurate motion control based on an external infrastructure that typically includes some highly sophisticated localization mechanism and a cluster of powerful backend machines that kind of crunch a lot of differential equations to represent the fine-grained behavior of the drone as it flies around. So the objective there is actually to study the microscopic interactions in the mechanics of these devices. And as a result of that is, for now, that kind of scenario is for now hardly applicable outside of labs. So the way I'm looking at this technology is more from the perspective of using drones as a mobile computing platform. And arguably, when we talk about mobile computing nowadays, what we mean is smartphones or personal mobile devices. But there's a key difference between this kind of mobile computing platform and aerial drones. Mobility in a smartphone system is something that is passively observed by the application. As we move around with the smartphones in our pockets, the applications kind of, for example, adapt their behaviors depending on our location, but they cannot influence the location directly. The key difference here is that in an aerial drone system, mobility becomes part of the application logic. So we can actually encode the mobile behavior as part of the application and combine that with whatever other functionality we need to achieve in terms of sensing or actuation on the real environment. And that's where things become interesting. So what I find really exciting about working in this domain is that it really pushes one out of his comfort zone. So many of the works that I'm going to talk about next lie at the intersection between computer science and engineering, automation and control, networking, computer vision, system identification, and towards the end of the talk, I'll be mentioning a project that is still to start, where we combine drone technology with human-computer interaction and even sociology, it's really the most fascinating aspect of working with this technology, the opportunity to combine all these disciplines together. So, as an example of the interdisciplinary nature of our work in this domain, I wanted to start talking about a piece of work that we published some years ago at Mobisis called Reactive Control. We were lucky enough to get the Best Paper Award and the SIGMOBile Research Highlight for that. So it all started from the observation, or from the fact that we were really happy with the performance of aerial drones a couple of years ago, back then. That performance is mainly dictated by the functionality that's implemented on what's called autopilot. The autopilot is essentially a piece of software that runs on an embedded board on the drone, where its only objective is to implement a control loop that, based on sensor inputs, including INU readings, the GPS location information, decides what are the settings to apply to the motors so that the drone can move in space in the desired way. This is typically achieved with some form of PID control. This is nothing super fancy. It comes out of established literature in automatic control. But it turns out that the performance we were getting out of range of autopilots that we tried out was not really something we were totally happy with. So we started to look more closely at what is that happens inside this PID controller on an autopilot. And we basically recognized something that wasn't immediately clear. So PID stands for proportional, integral, and derivative. But if you look at the way the PID control logic is implemented in an autopilot, what you recognize is that the proportional component is basically dominating over both the derivative and the integral component. This is because, for example, if your navigation sensors are accurately calibrated and the weights are balanced on the drone, these two factors do not really bear a significant influence on the operation of the autopilot. Whereas it's the proportional component that is really dominating the operation of the autopilot. Now, if we include, if we take this observation into account in the operation of a time-triggered PID controller, we come to two key conclusions. First is that if it's only or mainly the proportional component to determine the control outputs, it is only the current sensor inputs that are important to decide whether the control output is going to change or not in the next control iteration. And second observation is that the control outputs are, as a result, likely to change only whenever a change in the sensor input also occurs at the same control iteration. So if we take these two together, these conclusions kind of represent an opportunity to make control more reactive than time trigger. Just hold on a second. Sorry, I had to close the door. So I was saying that these two conclusions that we have come from the observation that it's the proportional component to dominate on an autopilot provide an opportunity to make the controller more reactive than time triggered. What do we mean by that is basically whenever there are no changes in the sensor inputs, we can keep the control outputs as they were in the next control iteration, because there's nothing that is likely going to change in the next control iteration if the sensor inputs remain the same or experience very little variations. And as opposed to that, whenever the inputs change, then that's the time when we need to recompute the outputs, because new sensor inputs will likely correspond to a variation in the control outputs for the same control iteration. So if we apply this to the operation of an autopilot, and we find a way to do it efficiently, we can reap a number of key benefits, because as I'm going to show you next, we can make the control more timely and adaptive while sparing unnecessary processing, because whenever the sensor inputs do not change, there's no need to rerun the control loop, because we know beforehand that the outputs are not going to change. And as a result of that, we avoid over-provisioning the hardware and the control rates and make a much better use of the available resources. So this is sounds easy, but it's not, because there are three key challenges that are to be tackled if we want to make this to work completely. First is, how do we detect those changes in the sensor inputs that demand to run the control loop because they will likely correspond to new control outputs? And then how often can we afford to skip a control iteration over time without losing control or affecting the stability of the system? And how can we implement all of this very efficiently? Because anyways, the autopilot runs on top of a very resource constrained piece of hardware. There's not much to spare, so we need to be very careful at how we implement this whole processing. So I'm going to focus on the first challenge here, but you're welcome to check out the paper if you want to know more. One important observation when it comes to tackling the first challenge is that it's not as easy as saying, okay, same sensor inputs, skip the control iteration because the control outputs are not going to change, because the control decisions may not change also when the sensor inputs do change, as long as those changes are limited within a certain range. So we call sensor trigger a change in the sensor inputs that does alter the control decision. Now the question becomes, how do we detect the occurrence of a trigger? At the beginning, we tried looking into the details of the control loops as implemented in modern autopilots, and we got lost because these pieces of software are very complex. They come out of very unstructured development processes. There's not much documentation available. It was basically a nightmare. So we eventually decided to look at it as a black box. That we model as implementing a random phenomena where the input are the changes in a single sensor reading, and the output is a Boolean value that tells us whether the control decisions are expected to change or not. Now, if you look at the control operation this way, you can model it using logistic regression, which kind of mimics very closely the intuition we might have on how this reactivity may actually behave. So whenever the input doesn't change or the changes are limited in magnitude, the probability that the control outputs are also going to change is small. Whereas whenever the changes in the sensor inputs are large, so in this part, the probability that we need to run the control loop and compute new control outputs reaches almost asymptotically reaches 1. So we have embedded this reasoning into our implementation of reactive control for drone autopilots by essentially checking how large is the magnitude of a change in the sensor input and comparing it against the threshold that determines whether we run control in the case we run the control loop in the case the magnitude of the input changes is returns a probability above that certain threshold, or conversely we keep the previous control outputs if the probability of demanding a new control iteration to compute new control outputs is lower than that same threshold. Of course, this plot is a generic logistic regression curve. The question is, how do we estimate the one that fits the operation of the autopilot on the drone? It turns out there are only 2 parameters that need to be estimated. And the way we practically achieve that is to divide the operation of the drone in 2 phases. First, we run a boot up phase where the autopilot is running in the traditional way at the pre-configured update rate. And that is useful for us to collect an initial data set that we use in the background to run a least square estimation process that gives us estimates for beta 1 and beta 2. As soon as we have them, the drone switches to the reactive control mode, where we do use the logistic regression curve to decide whether we want to run control or not. Of course, we may have false positives during the operation. Those will be collected while the drone is flying and fed back to the next round of least square estimation that happens periodically as the drone flies. We have been, checking out how this whole idea was performing in a range of different settings. We checked very different kinds of aerial drones, from like big hexacopters to like more exotic configurations. This is called the Y6. You don't see it often. It's composed of 3 arms with 2 propellers at the end of each arm, and the 2 propellers are spinning in opposite directions. And you can imagine how the control logic on this thing is probably very different from the control logic that happens to run on a hexacopter like this. But we have demonstrated that this idea is applicable in all these settings, as well as as a kind of plug-in component in a number of different existing autopilot implementations, from Autopilot to Clean Flight and others. So the paper has a number of charts and includes quantitative evidence of how this idea performs during real flights. What I want to show you here is actually a video that was gathered when running reactive control. This video is not post-processed. It was shot at a time where flying above Milano downtown didn't require lots of authorizations that it is actually now. But what I want you to appreciate, hopefully Zoom doesn't affect the quality of the video too much. What I want you to appreciate is how stable is the video. Again, without any post-processing. And that stability is achieved because reactive control allows the autopilot to run only whenever there is a need to compute new control outputs, whereas resources are instead spared at the time where the sensor inputs do not change too much. And then those resources become then available perhaps at a later time where it is needed to, for example, counteract the effect of a wind gust, or the drone is flying through a pressure gradient. All right, so this was first work I wanted to talk about. The second is called IDOS. IDOS stands for Internet Drone Operating System. Here we're looking at a different problem. The problem we are considering now is the fact that with the advent of high performance wireless networks like 5G, we are in fact able to achieve a sort of end-to-end computing continuum where technologies like 5G act as a networking substrate connecting platforms from very resource constrained devices up to big machines in the cloud. In addition to that, 5G supports the mobility of the end devices. So the devices that are more likely to be carried around by the users can roam unconstrained because 5G is able to maintain that high performance no matter how, or at least in the best, hopefully no matter how the user moves around. 5G is also one of the technologies where concepts like network slicing are available, and therefore applications can reserve resources in advance so that they can operate with guaranteed performance. The question we wanted to explore is how do we make best use of this when developing drone applications? So the non-trivial drone applications usually span both the drones and the backend, because it's often the case that the application processing is so complex that you cannot really run it entirely on the drones. You need to rely on some more powerful machine on the back end. And then the development becomes more complicated because Right now, it is mainly the development effort that dictates where a programmer is going to place what application component across this continuum. On one hand, placing application logic on the drone is quite an ordeal, because we usually have like constrained resources on that device. And even more importantly, this a priori allocation of application functionality across the continuum is not to be carved in stone, because as the network performance changes over time, as the reliability or available bandwidth varies, as the devices move in space, the allocation of the different functionality across the continuum may need to be adapted. Right now, this is not really possible. Most of the existing applications are characterized by a lot of manual operation and one-off implementations that are basically very tightly adapted to a very specific deployment scenario. So IDOS is a system support layer that tries to remedy this situation. The idea is that programmers will implement applications as loosely coupled components that can exchange data through what we call a data bus layer. Some of these components may be initially deployed on the drone, whereas some other components may be initially deployed on the backend. But IDOS allows these components to migrate across the computing continuum. Components are internally structured as software actors. We are borrowing from the vast literature on the actor programming model, with some adaptations required, for example, to let the programmers decide what slice of the component state needs to be migrated together with the component whenever IDOS decides that a better deployment configuration is available. So some of these components need to be moved across the continuum. What you see here at the bottom is also the fact, represents the fact that IDOS allows more traditional components to be connected to the IDOS-based applications through protocols like MQTT and HTTP, but this part is there mainly for backward compatibility. I already mentioned how the components are internally structured. They interact with the data bus via pattern matching. So the data is typed, and the actors specify conditions on the structure of the data to receive data from the data bus. To make things even simpler, we also provide an API for writing or removing data from the data bus, rather than just placing or pulling data from the data bus. This kind of slightly deviates from the traditional actor model, but we thought was gonna be useful anyways. So the most interesting functionality here is migration. So how does it exactly happen? IDOS provides two kinds of migration functionality. One is what we call micro-migration. When using micro-migration, IDOS allows individual functions inside the components to move across the continuum. This is most useful when programmers want to achieve rapid migration of small functionality, for example, because they want to counteract short-term network fluctuations, and it's implemented using dynamic bytecode shipment and linking on the migration target. The underlying assumption in this case is, however, that there is an IDOS instance already available whenever we want to migrate the function, ready to accept the to be migrated function. The other kind of migration that we provide is called instance migration, and is there basically to overcome these the assumption of having an IDOS instance already running on the other end. With instance migration, we basically pack an entire IDOS instance together with all the components that it was running at a certain point in time and move the entire thing across the continuum. This, of course, incurs in longer delays. It's most useful not for short-term changes, but for more permanent changes in the deployment scenario. For example, whenever you know that a node is going to be shut down and it won't be available anymore for running parts of the application. And we use container technology for that. We have ways to create container images on the fly and move those across the continuum. We have used this system in an experimental 5G deployment in a project together with Vodafone Italy. What you see here are 3 drones flying next to each other in Politecnico campus. What you see here, the kind of paper roll type thing that was attached at the bottom of the drone, is one of the early 5G terminals that Huawei, which was a partner in the project, provided. This place is covered with millimeter wave technology. So all through 5G, all the drones could run IDOS and dynamically migrate perhaps the most time-critical functionality that you can think of, which is the autopilot, exactly what I talked about before. With IDOS and the ability to micro-migrate the functionality for running the autopilot, these 3 drones were basically running the autopilot on behalf of each other. And at every 5 seconds in this video, they were changing who was running the autopilot for who else. What you can appreciate here is that migration happens totally transparently. There's no, it doesn't bear any effect on the stability of the flight, at least as long as, at least for what you can appreciate from the video. So the last piece of work I wanted to discuss today is called FlyZone, and it's a testbed that we have developed because, again, we felt the need for something different than what the existing state-of-the-art was able to provide. This was published at Mobisys 2 years ago, and the original motivation was that at some point, an oil company came to us and asked, can we use drones for running inspections inside oil tanks? These places are GPS denied. You cannot use GPS for autonomous flight in there. So we thought to run some form of SLAM functionality there. And you certainly know that SLAM and all other similar functionality are widely researched. There's a huge literature about those things. What that literature kind of overlooks, however, is the fact that to make it work for real, you typically need to fine-tune the parameters to the specific deployment scenario. So you might have a very efficient SLAM implementation that works in your lab, but going from there to an oil tank is quite a feat. We tried that, and we've broken, uncountable drones, propellers, frames, and whatnot. So we thought we cannot do it like this. Let's think about how we can build something that is useful for us in developing this application, and perhaps also to the larger community in addressing similar challenges. So the challenges here are that, as I mentioned, there's typically quite significant hardware and or software customization that needs to be applied to existing implementations to make them operate in a scenario that is different than the one they were initially developed. There are simulators, of course, but they kind of fall short of expectations because they tend to use simplified models. Most simplified models of devices and environment. Most of them are actually designed for studying swarm behaviors, not really like sensing applications like in this case. And there are testbeds available, but those are the kind of testbeds that I mentioned at the beginning, focusing on the fine-grained mechanical control, not on the development of a full-fledged application. So FlyZone tries to make things better in this area, and it's designed with application-level experimentation in mind, with the idea that developers should be provided with ways to emulate a certain target environment. Emulating a target environment means, for example, having the ability to say, okay, what happens to my application if the drone flies through a wind gust? Can my application react fast enough? What would happen if my drone would fly through like a pressure gradient? And of course, while we're experimenting with all this, we don't want to break things. So we want the testbed to be able to protect the drones and people and objects around in case anything that we didn't expect happens during the development. FlyZone is a testbed that achieves these objectives by adding a little bit of software and hardware on both the ground control station and the drone itself. On the drone, we add a second computing device, can be as simple as a Raspberry Pi, running a custom software stack that communicates with the autopilot software through a serial interface that uses a protocol called NavLink. On the ground control station, there's an experiment script running that communicates with the FlyZone software on the drone. And through this link, the experiment script controls the drone to emulate the specific features of the target environment that we want to experiment with. How do we make the drone behave as if it was subject to certain environment influences? We have two ways to do that in FlyZone. One is based on a coarse-grained model that essentially considers the drone as a single point in a 3D space with the whole weight concentrated in the center of mass. As a result of that, it ignores everything, including like drag, inertia, and all the features of the specific body shape. The alternative we offer is a detailed model that is based on a one-time estimation of the key drone parameters, like the body weight and the drag coefficients, and uses the Newton-Euler methods to faithfully represent the drone dynamics. And we have created a full-fledged semi-automated parameter estimation pipeline that makes it easy for a testbed user with his own drone to plug it into FlyZone. We have used that pipeline, that parameter estimation pipeline ourselves, and in the current distribution of FlyZone, I'll come back to that in a moment, we have ready-to-use models for 24 drone types, including essentially almost the entire DJI lineup. So if you're using a DJI drone, for example, you have everything ready to be used in FlyZone. If you have your own drone, you use our pipeline to estimate the parameters so that the testbed can accurately control your drone in order to emulate the influence of the environment. The other major problem we had to face is localization. Localization is, again, a widely researched topic, but the requirements we are to address in the case of testbed are quite different from application level localization. So for testbed operation, we want, of course, highest precision and speed, if nothing else, because the localization information are input to the drone models to accurately emulate the drone behavior when it's facing some environment influence. The testbed can be fully instrumented. There's no problem in putting whatever we need in the testbed. It's a testbed after all. It's not the target application, and it must be interference-free because the application may have its own localization system and say it uses ultra wideband, we don't want to mess with that because then the testbed would actually influence the application behavior. We have come up with a custom visual technique to do this kind of localization that uses specific markers put on the ground and read by a camera that we have installed at the bottom of the drone. The patterns you see here are not random, of course. We have algorithms that can tell you exactly what kind of pattern you need to generate given the physical size of the testbed you want to install to maximize the accuracy and achieve the highest processing, the lowest processing latency in reading these patterns. We have tested how the combination of all this functionality works. The kind of experiment we have done proceeded this way. So say this is the testbed area. First thing we did was to rent wind machines, the kind of machines that are used in professional filmmaking to create wonderful wind effects. We placed a number of them all around the testbed, and we have placed digital anemometers in the middle of the testbed area. With a certain configuration of the wind machines, we have recorded through the anemometers the wind map inside the testbed area. So a representation of how air was flowing through the testbed area. Then we have removed the anemometers and let a drone fly through the testbed, subject to the same influence of the wind machines. We have tracked its movements through an OptiTrack system that we had co-located with the testbed, and that was our ground truth. So the specific movement in the testbed flown by the drone when subject to a certain configuration of the wind machine is what we wanted to emulate through FlyZone. To check that, we have removed the wind machines and then asked the FlyZone software stack to recreate the same flight pattern by emulating the influence that the wind machine would have if the drone was subject to that same influence. And the net result of that is that, depending on what model you use, we were able to achieve quite accurate reproduction of the drone behavior through the testbed. In particular, you see that the approximate model kind of increases in terms of root mean square error as the wind speed, the configuration of wind machines creates stronger and stronger wind patterns. But with the detailed model, we can stay within a 20 centimeter root mean square error. It means that the trajectory of the drone, when controlled by FlyZone, is at most 20 centimeter off compared to what the trajectory that the drone would fly if subject to the actual influence of the wind machines. If you're interested in doing this kind of experimentation for your application, you can build your own instance of FlyZone, because we have gone through the whole, we have created this architecture in a way that was not useful only for us, but for the larger community as well. So everything is actually released as open source, hardware and software. And all the scripts and tools that we use, for example, to create the patterns of markers on the ground for running the localization are also available. So if you know where you want to put your testbed, and you can measure, how large it is, how high it is, and a few basic, you can gather a few basic measurements there. You input all those information, and our tools will spit out what you need to print, go to the print shop and print to run your own instance of FlyZone. Right now, there's actually 3 of them. There's one at Politecnico, there's one at the University of Virginia, and one at Worcester Polytechnic Institute, and they're all very different from each other. So I want to conclude with a quick glimpse on a project that is about to start, but it's interesting because it again gives you a feeling of how interdisciplinary this work can be. This project is called the Drone Arena, and I want to start talking about it, showing you a video of an experiment that we have carried out in another project, where the objective was to study the unfolding relationship between an actor, a professional theatrical actor, and a flying device. The actors, as you can see in the video, the actors' bodily expressions influence and are influenced by the drone movements. And there is a sort of developing connection of some kind that creates, as the actor, who is not a trained drone pilot, tries to interact with the drone on an opera stage. In this project, we wanted to push the envelope and go past this point, creating what we call the digital future drone arena. So a concrete and conceptual platform that is useful for interdisciplinary investigation at the crossroads between mobile robotics, autonomous systems, machine learning, and human-computer interaction. We have three goals in this project. First is to build a new aerial drone testbed by further developing FlyZone that is expressly conceived to give sociologists tools to study these relationships. We will be using the testbed to run 2 drone competitions. The competitions will involve multiple teams that will be tasked to realize functionality that somehow push the state of the art. The first competition will be traditional in scope. The participating teams will be invited to program drones to navigate an obstacle course in the shortest amount of time possible. Whereas in the second competition, we want to do something exotic. We will take inspiration from the postures, from the posing, and the aesthetics of fashion shows, and we will use that as a motivation for asking the teams to implement gesture-based autonomous drone control, hopefully allowing us to explore a richer patterns of movements. And based on these competitions, we will conduct empirical investigations of the interactions between drones and humans. And these will include observations, interviews, microsociological video analysis that will then seed the work in the drone arena as we move on. And we can't believe this is a one-of-a-kind platform. Fashion is definitely not the only domain where the results of this project will hopefully be useful, because there are certain traits, certain characteristics and patterns in the interaction between humans and drones that even though we study with the excuse of a fashion show, can be translated to other domains. And if nothing else, the interest in this kind of investigation is testified by the fact that Prada Group actually is endorsing us in running the second drone competition at the end of the project, because they are themselves interested in how to use this technology in their own domain. Okay, this concludes my talk. I apologize again for the background noise. You might probably be hearing my daughter screaming. This is, of course, not a one-man show. There's a number of people that I need to thank that we're involved at different stages of the work. And I'll be happy to answer any question right now.
Okay, thank you so much, Dr. Mottola. That was a fantastic talk. A lot of, I guess, obviously cool demos. I guess we all enjoyed, so a virtual applause. So I guess we can actually now have questions. Edward, if you want to go ahead, please feel free.
Sure. Thanks, Luca, so much for the presentation. I especially really like the.
It's a pleasure.
I really like the video demonstrations. I think, in an area with so many so many papers, but so few demos. Really just so nice to see very impressive ones. I wanted to get to your comment when you first started about how drones really shouldn't be called robots. They just were not there. They don't have the autonomy and so on. But yet your work seems to be getting us in that direction. That if you can do SLAM and you get them stabilized and so on. So what do you see as the hurdles moving forward till we call a drone and maybe group of drones just true aerial robots at our command?
I think there are two major hurdles in that direction. First is, which I think, or I hope, was implicit in my presentation, is the fact that there's a quite striking disproportion between the literature that is out there and how much of real experimentation we have in the wild. As long as we don't try and move the stuff that we have been running in our labs out there, there's not, overall, it will be hard to kind of achieve those kind of visions that many are kind of, hypothesizing at this stage. And I understand it's a pain to do that. I've been there multiple times, and the amount of effort that you need to put in there is incredible. But it's kind of a required step on the way to really have autonomous drones flying around. As a consequence of that, if we want to put things out in the wild, we need to be allowed to do that, and that's the other major problem. Right now, the current legislation is essentially chaotic. The amount of paperwork and the time it takes for getting flight authorizations is incredible. And what's worse is the fact that if you want to do that for research, so you cannot guarantee that your system is bulletproof, and it's very hard to obtain those authorizations. You have seen our 5G experiments running on our campus. I can tell you a little anecdote about that. We have been able to get the authorizations to run the 3 drones in that area because on that Politecnico campus, we used to have a heliport. So in terms of regulations, that place was already authorized for flying devices. Okay, it used to be like a traditional helicopter. Now it's a much smaller aerial drone, but that made things easier for us to get the authorizations because we were able to basically skip a number of steps in the process. And we eventually convinced the Italian Innovation Authority that we were not doing anything super terribly risky. As you can see in the video, there's not much that the drones are doing there. They're going up and down, and that's not because we wanted to do that. That's the only thing we were allowed to do. And of course, if I want to try out something more complex right now, I simply cannot. And it's that's a major obstacle.
Thanks very much.
Okay, so I guess Joe has a question. Joe Cavallaro. Joe, would you like to go?
Sure. Yes, enjoyed your talk. Very interesting. The FlyZone software was quite interesting structure. I wanted to ask a little bit about that. You had designed that for that oil tank application, I assume. So there's a lot of 3D issues with that. I was having a little trouble relating your 2D floor maps to how that would express the 3D, and were you able to actually go back into the oil tank and use FlyZone to actually verify that particular scenario?
No, actually, I mean, I've shown everything in 2 dimensions only for illustration purposes, but the whole thing actually operates in 3 dimensions, including the drone models and how they're used to emulate the influence of the environment onto the drones. Of course, there's admittedly there are a few things that we couldn't emulate exactly as if they exactly as in a target deployment. One thing is, for example, the ground effect. Whenever the drone is getting closer to the ground during a landing operation, that step we cannot emulate with FlyZone, because that's essentially the boundary condition for the model we have, because the ground effect is not represented in the model. So whatever you emulate in FlyZone is limited to the operation of the drone at a minimum height from the ground. If you need to experiment with like very specific landing mode, that you cannot do because we don't have the models to represent the ground effect. That's one example.
Is there like a minimum feature size? I mean, I was trying to get a sense of the size of the drone versus the features or the obstacles you're trying to avoid. Is there some relationship there that you're able to develop?
So what we have, our experience so far is included using drones that are more or less the size of the one in the picture, which is like 30 centimeter size. And the obstacles are, if I'm not wrong, the smallest obstacle we have experimented with is half that size. Okay. There's again an inherent limitation there. If we go back to the architecture, we need to put another computing unit on the drone. There's no way we can do without that. That's not possible, for example, on a nano drone that is like, I don't know, 7 centimeter size. We've been playing around with those as well, but they're not using FlyZone because there's no way to use them in there.
Thank you. Thank you very much.
Okay. So Ashu also has a question. So Ashu, go ahead, please.
I wanted to echo everybody's comments so far. Great talk. Very, very nice. I had one quick question. In the operating system work, I think I forget the exact name. I think it was the second topic you mentioned. I guess all this all that requires real-time guarantees, right? Because if you want to operate a control loop over a wireless link on another device, is the operating system doing that, or that's the programmer's task? Is it basically a real-time operating system of sorts?
It's running on top of RT Linux.
I see. Okay.
So
all right.
We the real-time part we don't really do anything about that, because we can rely on RT Linux to implement that.
Okay.
This is not an original choice. In many cases, actually, drone systems use RT Linux or some derivatives for implementing real-time tasks. We just went with the flow and used that.
Yeah, no, makes sense. No, makes sense. It's already work done, so best to leverage it. Okay, great. Thank you.
You're welcome.
Okay, so we also have a few other questions from the audience. I'm going to read them. They're in the Q&A. So first question is from Mariam Khalid. She thanks for the great presentation. The question is, can you comment on how FlyZone can be deployed for multi-drone scenario with focus on investigating the drone-to-drone communications?
Actually, that's a good question. I haven't mentioned it in the talk, but FlyZone also has support for running multiple drones simultaneously in the testbed. One thing we have explored with that, for example, is dynamic antenna steering for creating a high bandwidth backbone between drones. That was a student project that was developed on top of FlyZone for the actual experimentation. So the experiment script. Oh, sorry. Let me quickly get to the architecture picture. Okay. Oh, yeah. So the experiment script here can control multiple drones, not necessarily one. So here you have a single entry point where you control the testbed operation of multiple drones possibly. For example, you can create certain flight patterns. You can check how the team of drones would adapt to like a certain environment influence that happens to apply to all the drones. You can do all those things.
Okay. Thank you. And then I guess last question, since we're out of time. Can you give us some applications about human-drone interaction?
One thing we are interested in is to understand better the interactions that happen between a professional drone pilot, who is normally a person who has gone through some formal training and obtained a license for flying drones, and the application domain expert that is there next to the drone pilot, trying to tell this person where to fly the drone, what picture to take, and how to point the camera to the object of interest. This kind of setup is very common nowadays. The operation of drones for like area inspections are offered on the market as services by drone companies that offer those services to non-drone companies. For example, we have the energy company here that routinely uses drone services of other companies, much smaller companies. And what happens in those cases is that the certified drone pilot comes to the premises of the energy company and then gets out with the domain expert, and they'll be there, elbow to elbow, trying to understand each other and interact with the drone to get the right picture that the energy company is interested in. All these interactions are very unstructured right now. And there are videos on the internet, even pretty funny ones, where these two people do not understand each other, and therefore the drone itself doesn't behave as the application domain expert would like. We are trying to shed some light in those kind of interactions between the humans and the drone. As in those cases, you can see the drone as a sort of extension of the human senses. Imagine the drone as an additional pair of eyes that you can control, but they're not your own. So how can you control those new pair of eyes that you got that give you superpowers to look from 500 meters up to whatever you want to take a picture of? So that's the kind of, I understand it's kind of fuzzy, but we have not started that project yet. And we have lots of ideas, and hopefully some of them will become more concrete.
Okay, thank you so much, Dr. Mottola, again, for again this wonderful talk, and also doing it at such a late hour at your end. We really appreciate it.
No problem. It's a pleasure.
So that actually brings us to the end of this talk. I would like to also thank everyone for attending. I guess we had like 35 attendants, which was great. I hope to see everyone on the next seminar. Thank you.